right, hello everybody. I'm Ulf Hansson. For those who don't know me, working with the power management team at Linaro. So this session is about device power management and how we deal with devices in the Linux kernel for idle management. So it's I have a couple of slides. I'm trying to walk through what's going on in the Linux kernel to deal with this, but feel free to stop and ask questions at any time. I don't have like super many slides, so I think there should be room for some discussions and some questions. So at any point. So device power management. So mainly in the kernel we have a couple of frameworks that's there to help for subsystem and drivers to deal with devices, and I'm going to walk through a couple of these frameworks and give an overview of how they work and what they can help with. I'm going to start with that, and then I'm going to move into some deployment and look at some corner cases and some good practices of how to actually do the deployment. So again, please ask questions at any point if you want to. So the system-wide power management framework we have, that's the typical scenario when we close the lid on our laptops, or so that means that you more or less close down the entire system in one go. You put the whole system in a low power state, and all the devices that you have in your system and resources in a controlled way. And you can do that from also internally in the kernel, and you can also there's also a mechanism to prevent this from happening. And that's in an Android case, for example. That's what they do, these wake locks things to actually prevent the whole system from going into sleep mode. So that's one of those frameworks. And this framework has a couple of low power states that it supports. One of the things you probably heard about this, but this is a list of the low power state that's been supported when you do this system low power thing. There's suspend to idle, suspend to standby, and suspend to RAM, and suspend to disk. So today this presentation is mostly focusing about the suspend to RAM and suspend to idle part, but yeah, suspend to disk is when you take a snapshot of your system and take that snapshot and store it in an image, and then close down the system entirely. And the next time you wake up, you look at this image and try to restore the state of the system. So there are some more complicated things going on there, but let's focus on the idle and suspend to run things during this session. So there is an interface, a SuSurface interface, where we can actually trigger this low power state to happen. And I've just listed it here for reference, but you can decide what state to go to, and you can decide when to go via this interface. As I told you before about this in-kernel way of putting it into low power state, it's called auto sleep, and you can also control that part from SuSurface. There's a link to a documentation there that gives more information about how the interface actually works. So some more details about how the sequence is happening. So we have something that we call a PMCore, which is taking care of all this. So it all starts out by someone is requesting the system to go to this low power state, and then there is a couple of I would say like system common activities that happens. There are some notifiers that we fire, and we're freezing tasks and freezing user space, and then we go into this device power management thingy that I'm trying to explain a little bit more about. So to control all devices in the system, we have a bunch of callbacks, more or less, device power management callbacks. And there is a whole plethora of them I'm going to show a little bit more about that later. But in principle, they are called in a certain order to be able to do things the way that is needed, more or less. And the PMCore has also a list of devices that exist in the system, and the PMCore walks through this list and invokes these callbacks per device in a control order, so to say. Sometimes there is a dependency between devices. You can have child and parent relationships, and you can have functional dependencies between devices, which we express in the kernel as device links. And these kind of dependency is also respected by the PMCore when it follows these things. So it makes sure to, for example, that it does not suspend the parent before it has suspended the child, for example, and so forth when you do the resume part. So these are the interesting callback when we talk about suspend to idle and suspend resume. Suspend to RAM, sorry. Regarding suspend to idle and suspend to RAM, there is quite a small difference nowadays. So in the suspend to RAM case, we are hot plugging all CPUs but the boot CPU. So only one CPU is remained online. That's the final thing that happens. And then there is a platform-specific callbacks that you invoke to do the final things, to put the whole system into low power state. For the suspend to idle case, you're instead using the CPU idle framework. So you put all the CPUs in the deepest state, more or less, that the CPU idle framework supports. So there's not big difference from device management point of view, or actually no difference. Any questions so far? Okay, moving into the next framework that is trying to help us. So the system-wide thing makes sense when you know everything is going to be powered off. I'm not going to use the platform now for a while. But there is also the other scenario where you actually have a running system, but you're not using the entire system. Parts of the system is not being used. Devices and resources are inactive. And rather than keeping all of those powered up in their full power state, we can just power them off that is not being used at the current moment. So typically you have some requests that's coming in, and you may not have requests at a certain point. And then it makes sense to power off these devices. That is the Runtime PM framework job to help with. So to deploy this support, that needs to be done on a per subsystem and per driver basis. And there is a bunch of interfaces here. There is a whole bunch of more interfaces, but these are kind of the important ones. So to start using this, you have to enable your device Runtime PM. That's the PM Runtime Enable call. And then there is both synchronous and asynchronous calls to resume and to suspend your device. And you can also do that by reference counting on this. So, and sometimes it's common for subsystem and devices that there is bursts of requests coming in. So rather than put your device into a low power state between each and every request, you can let the device stay powered for a while, and when there is like an inactivity for a certain idle period, then you put it into a low power state. So that's these auto suspend interfaces that helps you with doing that. And there is SuSurface interface to actually control whether you want the device to stay always resumed or if you want it to be dynamically changed. So that's it's there mainly because of bugs, I would say. Some devices didn't really work out well, so we need to they need to stay powered on always. Well, so the more interesting thing is probably the stats and states and stats, I would say. So you can actually see over time, for example, how long a device has been suspended. and how long it has been active, for example. And you can also see the current state of the device. Some of these stats are not available by generic def config, so you might need to enable this advanced PM debug thing to get more information there. But these are interfaces that can be quite interesting to see when you start. Well, if you start deploying yours, support for this is really helpful, I would say. So in the Runtime PM sequence, this is like the typical scenario. What is happening at some point? You have some work to do, and you want your device to be powered on, and then you call this PM runtime get sync. And after that point, there is a callback being invoked for the device that allows you to resume or power on the device, more or less. And then you do the work that you need to do, and when you're done with the work, you want the device to go into low power state, and then you call this put functions. And at some point later, depending on what put interfaces you're using, asynchronous or the idle period thingy, auto suspend, then your callback, runtime suspend callback will be invoked and let you power down the device. All right. So now we have these two very nice frameworks that you can play with, but things get more complicated than so. Sometimes devices are grouped and sharing power rails and whatnot, complex hierarchical topologies that exist, and so more or less sometimes we need to control devices together, power manage them together. We have these buses and types which make sense for the same kind of devices, but there might be even cases where different kind of devices actually also needs to be controlled together, and that's what we have these PM domains for. So just to show you a little bit, this callbacks I've been talking about, it's just a struct dev PM ops, and there is a whole plethora of callbacks in there. Yeah, some of those are for system-wide and for runtime, system-wide suspend, and the other one for a runtime suspend. But the thing is that you can do this in a hierarchical way. So the struct device has this dev PM, PM domain pointer, and the bus pointer and the driver pointer. And on each of these levels, you can have these dev PM callbacks assigned, which means that a struct device can share the PM domain. It can have the same PM domain as another struct device, which means that it will share these dev PM callbacks, which in the end means that they can be power managed together. So there is a couple of implementations of PM domains, and there is this CPI PM domain, and it's widely used on x86 platforms and some ARM servers. So the thing is with this PM domain, it's a very centralized way of dealing with power management, and all of things is happening in firmware. So on the subsystem and on the driver level, if they want to implement Runtime PM, all they do is calling get and put, more or less, to notify for the PM domain that I need my device to be powered on now because I have some work to do. But in the lower layers of the subdomain and the driver, there's nothing else but calling get and put. There's no clock management happening in those layer of callbacks. Everything is taken care of in the centralized ACPI PM domain. So I'm not going to talk more about that. That needs more time for another subject. Instead, I wanted to spend some time talking about the generic PM domain, which is the one I'm maintaining as well. So this is more of more a flexible solution for dealing with PM domains. You can have both controlling devices together on the PM domain level, but you can also let devices being power managed on the driver level. So it allows a greater flexibility than the ACPI PM domain. And it's widely used on ARM SoCs today. So what it does is that if you have these complex topologies where you have devices being hooked up to various levels or in the hierarchy, you can all describe that in device tree, and you can say that this device belongs to this PM domain and this device belongs to this PM domain, and you can even have PM domain saying that my PM domain is a subdomain of that PM domain. So you can actually allow us to describe the system in a quite nice manner. So that's what the generic PM domain is all about, helping you to model the topology of the system. Yeah. Any questions? So yeah, this is what I was talking about. You can have a couple of devices sharing a power rail. In this case, I'm calling that a PD slave domain. They might share a power rail on that level, and then they might have an additional rail to share with something else. So it can be that PD slave domain can have a master domain on top of it. So all this can be described in DT. So yeah, there's bindings described for this that you can go and have a look at. So especially when it comes to runtime PM, obviously if you put devices into low power state, they will have to be woken up when you need them. And waking up does not always come for free. It might consume some time, which introduces more or less request latency. So in many cases, that's fine because the latency is more or less ignorable. But in some cases, it isn't. So there's a couple of options that you can use to mitigate that issue. And one of the things we already discussed, that was this idle period when you have bursts of requests and use the auto suspend feature. But yeah, in worst case scenario, you don't accept any latency at all. That means that you more or less has to keep the device always resumed, and then it's just a matter of taking another reference count for the device, so it stays on all the time. But there is also a third option that is on the NPD level, generic power domain level. There is actually a governor that you can hook into a power domain. So, which means that when you have a device dropping all its reference counting, saying that I'm about to go into a low power state now, the runtime suspend callback is being invoked for me. Then on the PM domain level, we can actually consider if there is any constraints from a latency point of view set up for this particular device. And then the governor can say, no, it's not fine. The constraint is not going to be met, so stay on, please. So that's what this NPD governor is there to help with. So just a brief overview of what's happening when you have NPD attached to your device. So you call this get function, and you end up invoking the highest level of the resume callback for your device, which is on the NPD level. Then the NPD will actually respect all the other layers coming down to even the device level, and you will be enabling clocks and doing the ping control stuff or whatever you have to do to power on your device. And but actually before you can go on and do that part, the NPD need to understand if this is the first device in my domain that it's about to be powered on, because that would potentially mean that the power rail for this shared, the shared power rail might be cut. So there's some internal keeping reference counting in NPD as well to understand this. So if that is the case, it will actually power on the rail if that's needed, or whatever is needed in this case. So then it walks down in the hierarchy, and when it's done, someone is calling put, probably the driver, when it's done with its request. And then all these things is reversed in the order back. Make sense? So about deployment then. So what I've seen throughout the years is that the common method to implement support for Runtime PM and system-wide suspend is that in most cases you start out implementing the system-wide support, so system-wide suspend support, which and then after a certain time you realize, oh, it would be nice to have Runtime PM support as well, so you add that on top. And then at a later point you realize, oh, I have this shared power rail, I need to deal with that as well, so you add that on top. That kind of works, it's no problem with that, but there is a smoother way of doing things. And rather than starting from the bottom to top, you can actually, it becomes easier if you start from the top to bottom, actually. So first of all, put the power rail and put the topology there. That's easy, and nothing will break. And then you add a Runtime PM support instead in the driver. Start with that. And the reason why I think it's useful to do that is because sometimes it's quite similar kind of operations that needs to be done from Runtime PM and System PM. And there is helpers that actually allows you to reuse the code that you have implemented for Runtime PM for System PM. So just an idea. So to deploy NPD support, it's just this is just like a bunch of items that is useful to follow. There's a lot of examples in the kernel of how you do this. So if you just do git grep for PMNPD init, which is the common function that's being called for all power domain providers, you'll see there's 36 callers of them. So there's a lot of reference that you can have a look at. But in principle, I would follow this in this order if I would implement support for NPD for your particular SoC or platform. So we have these two frameworks, and we're trying to make them play together. And there is a couple of situations that we have observed. As I said, sometimes putting a device into a low power state is very similar between these two different frameworks. So going into runtime suspend is very similar as going into system suspend from the device point of view. So that said, obviously we don't want to duplicate a bunch of code. We want to minimize open coding, of course. So that's one of the observations. The other observation is that we don't really want to power on devices in the system suspend phase unless they are already if they're already in a low power state from a runtime PM point of view. Why should we power them on just to power them off again? There's this kind of tricky scenarios that you have to, these more or less these two frameworks need to play together. And the goal is obviously to avoid wasting energy, but also to decrease system suspend resume time. So there is a couple of different ways to do this, and one of the ways is to use this runtime PM-centric approach that we have been promoting a little bit within Linaro throughout the years. So I'm just showing them very easily how how this is fixed. So there is two helpers that's called PM runtime, force suspend and force resume, which are more or less wrappers of your runtime PM callbacks. So in the easiest scenario, when you have the exact same kind of operations that you're doing for system suspend as runtime suspend, instead of duplicating this, you're just assigning your system sleep callbacks to these helpers, and they take care of this. They look at the state of the devices, and if it's already in the correct low power state, it just leaves it like there. And it also checks that when it's resuming the device, system resuming the device, it checks that is it okay to leave it in the low power state for now? Do I need to power it on immediately, or can that be deferred until there is actually a request later on when the system has resumed? So this helpers tries to cover that for you. So there's a lot of good examples. There's around 140 users of the kernel of these helpers nowadays. So there's a lot of references that you can have a look at. A couple of words about Wakeups. I've more or less just skimmed through that during entire talks, but obviously when your device goes into low power state, sometimes you have some external wake up for your device. So from the runtime suspend point of view, those kind of wake ups always needs to be enabled, of course. But for the system low power states, it's different, because you may not want to wake up, or you may not be able to wake up, depending on the system. So a couple of different scenarios I've listed here, and so I would say the most important takeaway from this is that if you do not support this wake up for runtime suspend, you have to keep your device powered on, which is kind of bad, but that's what you have to do if you have wake-ups that you cannot control without keeping the device powered. There is a helper function that you can use to deal with wake-ups. This dev PM set dedicated wake RQ. It helps with dealing with these different scenarios that is happening during wake-ups, but it also informs the PMCore during the system suspend phases, that all of a sudden during the phase, for example, when you're doing the system suspend thing, there might be some wake up being signaled for some of the devices. Then the PMCore can actually monitor that and bail out, so rather than doing the full suspend path. So some of those things are is taken care of behind the back, so to say, when you are using this helper function. All right. So for the system wake-ups, I mentioned this briefly. There is a couple of APIs where you can actually the system wake-ups needs to be configurable from user space. So sometimes user space wants to inform that I'm not interested about waking up by this device, or I may be interested about waking up with this device. So these APIs I have listed here helps to control that. So the device init wake up is often called during probe of a driver to actually inform user space that my device is wake up capable. And then the device may wake up interface here is the one that's being called during the system suspend of your device, and that takes into account what user space has decided to do. All right. If you mark your devices as wake up, this the system wake up capable?
Yeah.
Yeah?
System wake up capable, but I haven't, for some reason I do not use the device in wake up and device may wake up anything else. What happens to it? It still can mark it since outside enable I to wake.
Yeah. There is a gray zone of what is okay to do, and what you will probably end up in some corner cases where it doesn't really work. So the real thing you should do is actually call device init wake. Otherwise, you will not be able to bail out, for example, in the system suspend process, if you not inform the PMCore that this is a device, capable device.
Is PMCore tracking what inputs belong to what devices?
Yes, from the wake-up point of view, yes.
I think that was my last question. Yeah. So you're saying that the PMCore is aware that an interrupt belongs to a device, and that device is being marked.
No, well, it doesn't really monitor IRQs on that level. It just monitors if device is device IRQ, so to say. So it doesn't really care about IRQs as such. But so if you have like enabled IRQs for your devices, and there is an IRQ being raised during the suspend case, that means that you will there will be an IRQ handle being called, of course, and that will set some kind of flag in this system. So the PMCore will check that on per device level during the system suspend phase, and it can bail out. So it doesn't really care about IRQ, but if this more or less if this flag has been set because of an interrupt being raised.
I see.
Yeah.
Okay.
Yeah. I guess we have to go into more details to really narrow down the. Did it explain? Yeah.
I think I get a big,
Yeah.
a high-level picture now. Yeah.
All right. I don't have anything else but this. Any other questions? So this was a very quick walkthrough of the framework. So if there's
You said in suspend to RAM case, one CPU remains online.
in the suspend to RAM.
The boot
right.
CPU,
Yeah.
right? What happened in the hibernation scenario when we take the snapshot?
So from the CPU point of view?
Yes.
Well, that's a good question. I don't know, actually. I'm guessing that it's very similar to suspend to RAM, but I'm not sure.
But
I'm not sure, actually. I don't
the
know.
boot CPU won't use the same callback as non-boot CPU.
So the question is, on the suspend to RAM case, we're hot plugging a bunch of CPUs, but the boot CPU. What is happening in the suspend to disk case? The same thing. The same thing, yeah.
But it uses different callbacks.
It uses different callbacks on the device PM callbacks level.
The Cisco callbacks, I guess.
The syscall callbacks?
The boot CPU uses different power offs, I guess.
Right, yeah. I assume so, yeah.
And the other question I was having is, so we have a runtime PM framework and the idle. So there may be the race condition, right? If both try to act on the same device, so who wins and how we solve this problem? In kernel, who takes care that the device is already suspended? For example, if the runtime PM is already suspended one of the device, and then idle thread comes in a picture and try to suspend the same device.
Can you bring the mic?
So my question is basically the race condition between the idle thread and the runtime PM, how it takes care of the kernel.
So the CPU is managed. The CPUs are managed completely differently from the devices. So when you do the suspend RAM thing, for example, you do all the device power management in one go, and when you're ready with that, you'll deal with the CPUs. So there should be no race condition in regards to that.
No, but when the system is running, right, So the runtime PM is active, and it might have suspend one of the device. And when everything is down, then the idle thread comes in, and he also tries to suspend the same device.
So the idle thread is only caring about CPUs?
The CPUs only?
Yeah.
Okay. Okay. Thank you.
And the idle thread will not come because the user space is frozen.
Okay.
But I think he's talking about suspend to idle, right? No?
Yeah, I mean, both the cases I wanted to.
So but we freeze user space along there.
So I mean, the idle thread is for the CPU, I assume.
Yeah,
Oh.
that's right.
Yeah. Okay. So user space has been frozen far away earlier. Yeah.
Thanks.
Okay. Okay.
Is there a way to list all the wake-up sources like in code/code?
Yes, I think there is. I don't know exactly at the top of my head how that. Okay. Okay.
So in your presentations, you mentioned that as you're going into suspend, either through runtime suspend callback or the system-wide suspend, it's legal to enable the wake-up aspect of an IRQ, but disable the IRQ at device level. So you mind going back to that couple of slides?
System wake-ups, right?
Yeah, so if you look at the suspend callback, your advice is we enable the wake-up aspect of that IRQ.
So what typically should be done in your suspend callback is that you will call device may wake up. And that will return true if user space wants this device to be wake up capable when it's been suspended.
Okay.
So if that returns true, you should call enable IRQ wake for the device, kind of.
And then the disabling, the next step there, disabling device IRQ, is that what the driver should be doing, or does that the suspend framework takes care of that? Your second bullet point, disable device IRQ.
That, I mean, if you're using this helper function, it might be, I'm not 100% sure about this, honestly, because it's a while ago since I looked into this, but the dev PM set dedicated wake IRQ might help with you with this automatically. If it doesn't, you have to do it yourself. Don't take my word for exactly how it should be done, but the point is that you have to disable the IRQ wake feature or of the device when you do system resume. So I know some drivers is calling this function themselves, and maybe this new helper it's a little bit new to me. I haven't really looked in exactly what's happening behind the back, so to say, but it might happen automatically if you're using this helper.
I see. Okay. I think it does happen behind the scenes, the suspend framework, as it.
I'm guessing so as well.
Yeah, it'll disable.
But I'm not 100% sure about it. So.
Okay. The next question was, when I wrote drivers a long time back, the enable IRQ wake we'd never remove the drivers. So we always did that at the probe function.
In the probe function?
Yes.
Wow, okay.
Because we knew that this is an important device, especially if it's a PMIC GPIO or a power key on a mobile device or things like that. We know this IRQ is super important. We have to wake up, and that's what we would do in the probe function. And your advice is to not do it in the probe function, but delay it until we actually go into suspend, because a user space configuration might disable the wake up aspect of a certain device.
Yes.
And that's where the device may wake up.
So there is another reason for that. Obviously, this is from a widely generic point of view. So the idea is that if you call this enable IRQ wake function, we can assume that some kind of electronic always-on domain gets powered on. So do you want that to stay powered on even when you don't need the wake up? So that's why we advise in general to enable arm the wake up when you go for in system suspend mode. So doing it in probe means that of course this is platform dependent, so it might not matter for you. But if you do it in the system suspend, you know that it will only be enabled when you actually need it.
I see.
Maybe he's confusing it with the other API where we say that the device is actually capable of wake up.
The capable of thing is the device init wake up. So device init wake up is supposed to be called during probe because that announce. So that announce. No.
Oh, well, maybe the devices I dealt with were super important. So regardless of what the user space setting was, I have to enable those wake up IRQs.
I know there is a couple of cases where actually there is another function that's called enable IRQ wake, I think only. So you can actually enable just an IRQ to be wake up capable without actually doing that for the device. There are some corner and gray zones around this, so
Okay.
it's been slowly evolved and modernizing this code during the last couple of years. So it's fairly recent with these things. So yeah.
I guess the device driver has to have this routine, enable IRQ wake and disable IRQ wake, because it's the driver who handles that IRQ, and he should aware of the count. If you just call enable IRQ wake and don't call the disable IRQ wake, then you probably get the unbalanced IRQ message.
Yeah. Are you saying that there's a disabled depth counting for the wake up aspect?
Yes.
Okay.
There is. So yeah, basically like how many times you call enable and disable, it should have in sync.
Okay. Got it.
You basically don't know where to start from. Basically, that's why.
Okay. Okay. Thank you very much.